So let's look at the periodic table. The periodic table is one of the most important tools in a chemistry class in working with anything in a chemical application. It is a roadmap that screams a whole bunch of information. But if you don't know how it's put together, you can't get the information. Just like if you don't know how to read a map, you're going to have a hard time navigating your way if your phone goes down and your GPS isn't working. Okay? So, I'd like to give you a reader's guide to the periodic table. So first of all, periodic table, what is it, or the periodic chart? It is an organized catalog, if you will, in one page of all the known elements and even a whole bunch that we have synthesized in a laboratory setting. Okay? And they're arranged by similar chemical properties. You may or may not be familiar with the story. There were a number of different scientists in the 17 and 1800s who, as elements were being discovered, they began to group ones that reacted similarly. But the modern periodic chart owes its basic structure organization to Dmitry Mendeleev, a Russian scientist who, in the process of trying to write his own chemistry textbook, which was something that was done in his day, needed a way to organize many of the elements outside the most common ones, and came up with a system, his based on atomic mass, the modern one now based on atomic number, that organized systematically in increasing size or atomic mass or atomic number the elements, but then ended up grouping them in repeating patterns so that in a column going down, all of the elements had similar patterns of reactivity. So, one way in which this all shakes out is there is what I always like to point out as the staircase. Some versions of the periodic chart have this very bolded, others it's really not there. But in this diagram that's on this slide, you can see that where that staircase that runs between boron and aluminum and then continues down and continues down and continues down, and sometimes it'll split between the elements that are in red. It's the border that distinguishes metals from nonmetals. What makes something a metal? As you can see, it's got those properties listed there. It's lustrous, meaning it's shiny. It's malleable and ductile, meaning it can be easily shaped, flattened into sheets, or drawn out into wires. And metals are all, to varying degrees, conductive of heat and electricity, some more so than others, but all of them have those characteristics. In chemical reactions, they tend to be electron donors, for reasons that will become evident as we go through the rest of this presentation. So they become positive ions. They lose electrons, become atoms with a positive charge, what we call cations. On the other side of the staircase, the elements that are in yellow are nonmetals. Most of them are either gaseous, brittle solids. There's only a couple liquids here, and one liquid, bromine, at room temperature. All of those elements tend to take electrons, or will share electrons with each other to form a whole class of compounds called molecules. And so they become negative anions when they interact with the metals, all right? And they're everything that metals are not. They're not shiny. They're not conductive. If they're even solid, they're not easily shaped. They're usually powdery or brittle or crumbly, or form network solids that have other kinds of properties, but they're not easily shaped. The ones in the middle, the ones that touch the staircase, the ones in red in this diagram, are called semimetals or metalloids. They have some aspects of metal properties, but other aspects that make them non-metallic. Some of these are what are then used for things like semiconductors, silicon, for example. Another organizational way to look at the chart The elements in gray in this diagram are considered representative elements. They play by the rule of 8. They follow something called the octet rule, because the electrons that are in their outermost shell, their valence shell, are filling the s and the p orbitals. And so between the s and the p orbitals, you have 8 electrons that are, or spots for 8 electrons. And so these are elements that are always trying to either get rid of the 1 or 2 or 3 they have, or get 1 or 2 or 3 more to get up to 8. And at the very end, you have your noble gases or your inert gases that are not reactive pretty much at all, with the exception of a couple of the heavier ones under extreme duress. Why? Because they already, helium has only room for 2 and is full with 2, but all the rest of them have 8 valence electrons. Their s and their p orbitals are full. Transition and intertransition elements are the things, like I like to say, between the goalposts, between the two rows of representative elements on one side and the remaining 6 on the other side. Transition elements have valence electrons that are going into the d orbitals, so now there are room for 10 more electrons. But d orbitals, as you may recall, overlap with the s of the next energy level until they're completely full. So they do this strange sort of transition, which is why they're called transition elements. Many of these elements, in order to become more stable, will give away not just one definitive number of electrons. In other words, they can have more than one charge state. Iron, for example, can exist in a +2 or +3 state and form compounds with things in either state that then give those compounds different properties. The intertransition elements, the ones that are at the bottom of the chart, I like to call it the pull-out section, because if you put them in there so you had one continuous chart, it wouldn't fit on one page. So they pull those out, put them at the bottom. Many of those elements are synthesized. They're of human creation, from accelerating smaller atoms together and getting them to stick together. Their valence electrons are filling the f orbitals. It's the f orbitals that are partially filled. And since there are 14 different possible spots that are f orbitals and at any energy level, then you have 14 different elements that are in that section. Now that you've kind of got an idea of where everybody lives, if you will, the neighborhoods of the chart. Now, here's where we come to understanding why the chemical behaviors are the way they are, and how it ends up being that things in a family, a column going up and down, have similar chemical properties. Elements in a column all have the same number of valence electrons, just at different energy levels. So the period going across corresponds to the energy level that's the valence level. The first energy level, second energy level, third energy level, so on and so forth. The first 2 columns of representative are S block, meaning the valence electrons are the S ones. And on the other side, that's where the p orbitals are getting filled on that energy level. D orbitals, because they overlap, always are one energy level behind the row that they're in the chart. So SC, for example, which is in the 4th period, that's a 3d orbital electron. And then the sections at the bottom, the intertransition ones, f orbitals overlap 2 energy levels behind. So you fill the 6s and then the 4f and then the 5d and then back to the 6p. Now, when we talk about trends, there are certain patterns going across the chart and going from the top to the bottom of the chart that we can describe. And they're all listed here on this slide. But they all come down to one fundamental issue. Electrons, remember, are negatively charged particles. The nucleus contains protons, which are positively charged particles. Opposites attract. Every electron wants to be as close as it can be to the positive nucleus, then it be in its lowest energy state. The problem is it doesn't want to be near any other like-charged negative electrons. And so every electron is sort of living in some sort of tension. There's one energy state, one set of waves and vibrations that electron is allowed to have, where it's as close as it can be to the nucleus, but also as far away from every other electron like it as possible. As you go from one energy level to the next energy level, electrons in lower energy levels sort of block or shield or screen out some of the positive pull of the nucleus from electrons that are in farther orbitals, that are in higher energy states. So the sweetest spot here in terms of pull of the nucleus, what we would call the effective nuclear charge on the outermost electrons of the atom, is with fluorine. Fluorine, the nucleus has a +9 charge, and there are only 2 electrons in the first energy level that kind of shield the effect of that +9 pull. So the other 7 electrons in the next orbital, in the next energy level, I should say, the 2s and the 2p's, are really screened off from that nucleus, only just a little bit. So fluorine is the most tightly, compactly wound element there is. It has the highest electronegativity, meaning its capacity to pull more electrons in. It has the highest ionization energy, meaning you got to put a lot of energy in just to pry one electron away because they're all held so tightly. It's the smallest atom going across in its row, and it's one of the tightest wound elements there is. As you move away from fluorine, going down its column of halogens and going to the left, heading back towards lithium, the amount of nuclear charge that's impacting whatever layer of electrons is the outermost, whatever the valence shell is, decreases. So that means atoms get bigger as you go away from fluorine. So the way we normally read things, left to right, atoms get smaller as you go left to right, because the effective nuclear charge gets greater. Even though I'm adding more protons, so the nucleus in effect is getting slightly bigger. Remember, atoms are mostly space anyways that the electrons are buzzing around in. So the amount of volume from adding protons is not that much. The effect of that nucleus on pulling the electrons in gets greater because I'm not adding electrons that get in the way of each other. They're all in the same energy level. As I go down a family, I'm adding a whole bunch of protons, but I'm also adding a whole new layer of electrons that are shielding that nucleus. So the valence shell is one more energy level out. It feels less attraction because of the electrons between it and the nucleus, even though the nucleus might be more positive. And so elements get bigger. It gets easier to remove electrons. They aren't as good at attracting electrons to them. All of the different periodic trends that we can talk about really boil down to the effective nuclear charge. The number of protons in the nucleus versus the number of filled energy levels of electrons that are screening or blocking or shielding that nucleus from the valence shell electrons. And so when you think of that and then look at each of the properties that we talk about are trends: size, electronegativity, ionization energy. If you read them sort of in that context, you can look at the chart and make comparisons based on where elements are and have a pretty good idea, even without having hard numbers, as to where they should fall or where the trend is, which ones would be easier to remove electrons from, which ones would be less likely or more likely to attract electrons in a bond. Okay, so effective nuclear charge is the key idea I want to leave you with. So to review, we've talked about how this periodic chart is organized into periods or rows across, which correspond to energy levels, at least loosely. How the columns are families where everything in that family, all those elements, react in a similar pattern because they have the same number of valence electrons just on successively higher energy levels. And then the neighborhoods, metals, metalloids, nonmetals, which have their tendencies and their behaviors in part because of how their electrons, especially their valence electrons, are attracted to the nucleus of those particular atoms. And where there's a greater attraction, they tend to form small molecules that are gases or network solids that may be brittle or may be very tough but not easily shapeable. Whereas metals, it turns out, their valence electrons are sort of very fluid amongst the nuclei and create a situation where you can kind of move them around and hold the overall shape of the structure of which those atoms are, which those atoms make up. So hopefully this gives you a little guide to reading the map of the periodic table.